Eye or love? AI, the next frontier. Hi friends, welcome to Xiaoliu X. Are you ready for magic? Today, we are exploring the magic stories into real cartoons and movies instantly. Imagine if you told a robot a fun story, and poof, it painted a moving picture for you right away. This is real magic. It uses a computer brain to listen to your words and make movie magic happen right before your very eyes. Before, the robot was dizzy and walked in wobbly lines to draw, but now it has a super map. It runs in a perfectly straight line, super fast, to make the perfect drawing without ever getting lost. And here is the coolest secret trick. Instead of reading a giant heavy book to find one answer, the robot uses a magic shortcut. It jumps straight to the right page to finish the movie. It makes the robot super duper fast and smart.
Welcome back to The Deep Dive, the place where we take a stack of dense source material and really just distill it down to what you actually need to know.
And today, we are strapping in. We're doing a massive dive into the Kandinsky 5.0 model family.
Yes, and this is a big one. It's all about open source generative AI, moving from just text to image to, well, making movie magic.
Our mission today is pretty crucial. We want to understand how this suite of models didn't just get a little better. It made a huge leap in engineering.
A leap from static images to generating complex, high-resolution videos. We're talking up to 10 seconds long at, what, 1408p resolution?
Exactly. This is really a technical story about hitting that high performance without, sacrificing open access.
Okay, so let's break this down. We've got some seriously dense concepts here. Diffusion transformers, flow matching, even something called model souping.
Right.
The goal for you, the listener, is to get a shortcut. We want you to understand the core breakthroughs that let Kandinsky go from a picture generator to a competitive video studio.
That's the challenge. It's about synthesizing three core breakthroughs. First, moving from older diffusion methods to the much more elegant flow matching idea.
Okay.
Then, harnessing the power of the crossed-ID architecture. And finally, the almost unbelievable rigor they applied to curating their training data. It's a system built for speed and quality.
And before we get into the engine, let's just frame the scope. This isn't one giant AI brain, right? It's more like a family of specialized tools.
Correct. Kandinsky 5.0 is all about versatility. You have the Image Lite model at 6 billion parameters for your text-to-image and editing.
Day 6.
Then you move to video. The Video Lite model is 2 billion parameters for, lighter, faster tasks. And then you have the flagship,
The big one.
Kandinsky 5.0 Video Pro. It's a 19 billion parameter beast that handles the really high-power, high-res 10-second videos.
Yeah.
Different jobs, different specialists.
Makes perfect sense. So let's start with that revolutionary architecture. Looking back, Kandinsky started in 2022, and it was drawing pixel by pixel, right?
Yep.
An autoregressive approach.
Yes. Then it shifted to diffusion models. But 5.0, this is the radical shift. This is where they embrace the flow matching paradigm.
Okay, so traditional diffusion, that starts with just pure noise, like static on a TV, and then takes hundreds of little steps to clean it up and find the image inside.
That's the key.
Yeah.
Hundreds of small, sort of wobbly, stochastic steps to reverse that noise.
Right, and here's where we need that explain it to a 6-year-old analogy. If diffusion is that wobbly path, how does flow matching or rectified flow change the journey?
It's like giving that whole process a super efficient mathematical GPS.
Ah, okay.
Instead of all those wobbly little correction steps, flow matching aims to find the straightest, most linear path from the noise, the start directly to the clear image at the end.
So a straight shot, no detours.
Exactly. No detours. It's less about guessing how to clean up noise and more about predicting the perfect trajectory to the finish line.
Which means faster generation and a more stable, higher quality output. Makes sense. But what's the engine running this whole refined process? That's the cross-D architecture.
The cross-die, or diffusion transformer with cross-attention, that's the core computational brain. It's designed to fuse everything it needs all at once.
Everything meaning what exactly?
The visual data, so the noisy image or video, the time steps, how far along the path we are, and crucially, the text instructions you gave it.
And that cross-attention mechanism seems to be the special part. Why is that so much more important for video than just a still image?
Because in video, consistency is everything. Cross-attention is the part that is constantly checking and rechecking the visuals against your text prompt.
Okay.
And make sure that the red car you asked for doesn't just, randomly become a blue truck 3 seconds later. The tighter that attention, the better the model follows your instructions.
The scale of this is just massive. The Video Lite model uses 32 of these processing blocks, but Video Pro, that scales up to 60 blocks.
It has to. It needs that power to handle the sheer complexity of those huge 1408p video files. It's an enormous computational footprint.
Which brings us neatly to our next segment. You can have the best engine in the world, but if you feed it junk fuel, you get junk results.
Precisely. Kandinsky's quality comes from ruthless data quality control.
Okay, so they start with hundreds of millions of images and videos, but that raw data needs, what do they call it, hyper-curation.
Yes. And this involved a multi-stage cleaning process, using other sophisticated AI models as gatekeepers.
I love that idea. AI models judging other AI's data. So what were the criteria? What were they looking for?
They needed to score the data on a couple levels. First, they used models like 2PIQ to judge the technical quality. Is it sharp? Is there a lot of noise?
The objective stuff.
Right. But then they also used a model called Q-Align to judge aesthetic quality. How visually pleasing is the composition, the color palette?
You're kidding. So it wasn't just, is this a clear photo, but is this a good photo?
Exactly. A dual scorecard for both objective and subjective beauty.
And they even filtered out images that were too simple. That seems backward.
It does, but it's critical.
Yeah.
If a model only ever sees simple patterns, it can't generate a complex scene. They use the SAM2 model and a Sobel filter to find and just discard overly simple images.
Like a plain blue sky or a solid white wall.
Exactly. They wanted complexity in every single sample to make sure the model learned deep scene understanding.
Demanding complexity from the very start. And they did the same on the language side, creating these incredibly precise captions.
To get high-quality descriptions for all those scenes, they used huge multimodal models to generate detailed synthetic English captions.
And the quality control was intense, I read.
Oh, yeah. Down to filtering out sentences that had any non-English characters like Cyrillic, just to maintain the language purity in the captions and avoid any confusion.
That level of detail is just wild.
Yeah.
Now, what about the image editing? The image-to-image models. They needed 150 million pairs of images showing a change. How did they find those?
This required a really sophisticated verification dance. It wasn't enough for two images to just look similar. They had to confirm an action happened. They used metrics like CLIP to see if they were semantically similar. It's still a car. But then they used geometric tools like LoftTR and Ransack.
To check the geometry, to make sure image A wasn't just a cropped version of image B, but that something had actually changed, like the instruction, open the butterfly doors.
Got it. They're teaching the AI what an instructional change looks like, not just a duplicate. Yeah. That's what unlocks that precise editing.
Okay, so that's the meticulously prepared input. Now let's look at what happens right before the final product, the advanced fine-tuning stages. It wasn't enough to just train the model. They had to soup it.
Model souping is a brilliant insight. They found that traditional fine-tuning was actually degrading the photorealism they'd worked so hard to build.
That is the ultimate counterintuitive problem. The final polish was ruining the paint job.
Exactly. So their solution was to compartmentalize. They created 9 separate mini-experts.
Right, for different themes.
Yes. They clustered their data into 9 domains people: nature, architecture, and so on. They trained a specialized model on each. And here's the clever bit. Instead of picking the best one,
they averaged them all together.
They averaged the weights of all 9 expert models. They souped them together.
That's amazing. You train 9 slightly flawed specialists, blend their brains, and you get a superior generalist that's more stable across all topics.
And the human evaluations confirmed it. The souped model showed a huge boost in quality. But they didn't stop there. They also added an AI critique phase.
This is where they use reinforcement learning to push for maximum aesthetics. This is the DRAF-T method. Tell us about this AI critic.
They trained a totally separate component, a reward model, to act as a quality judge. Its only job is to compare 2 images made from the same prompt, say a generated one versus a real high-quality one, and just learn to prefer the better one.
So the critic learns the difference between good and great.
Precisely. And once that critic is trained, the generative model is then tuned to maximize the chance that the critic will say its output is better.
It's a relentless, perfectly objective feedback loop.
It is. It pushes the model toward realism and beauty way beyond what standard training could ever do.
It sounds incredibly powerful, but also incredibly intensive. If every pixel has to talk to every other pixel, especially in a high-res video, How do they stop the whole thing from grinding to a halt?
That leads us right into performance, speed, and the trade-offs.
Yeah.
You've hit the nail on the head. That quadratic scaling complexity of video attention is the bottleneck.
So how did they solve that for these long 10-second videos?
They implemented a proprietary solution called NABLA. That's Neighborhood Adaptive Block Level Attention.
In simple terms.
It's sparse attention. If standard attention makes the computer look at every single block of pixels for relevance, NABLE teaches the model to just look at the most relevant blocks for any given calculation.
So instead of reading the whole book to find one answer, it just looks at the table of contents and jumps to the right chapter.
That's a perfect analogy. And by doing that, they accelerated training and inference speeds by up to 2.7 times for those really big jobs. A massive leap in efficiency.
A 2.7x speed up just by being smarter. But they also created dedicated speed models, the Flash variants.
Correct. The Video Lite and Pro Flash variants are aggressively distilled for extreme speed. We should define a term here. NFE, Network Function Evaluation. It's basically one computational pass.
Okay.
The standard models need about 100 NFEs. The Flash variants,
How many?
they cut that down to just 16.
Wow, that's a huge reduction, 6 times faster.
It makes them immediately useful for rapid prototyping or running on lower power systems.
But there's always a cost to that speed. What's the trade-off?
The human evaluations show a measurable but generally moderate drop in performance. The main thing that gets affected is temporal coherence, making sure movement looks right frame to frame, and some of the fine detail.
So you get speed, but you might lose a little bit of that perfect polish.
Exactly. It's a choice for the user, speed or maximum precision.
Speaking of performance, how did the standard Kandinsky 5.0 do against its big competitors in those human evaluations?
In the side-by-side tests, Kandinsky 5.0 Video Lite was consistently preferred over major competitors in 2 key areas: visual quality and motion dynamics.
So people thought it just looked better and moved more realistically than models like Sora?
Yes. Raters judged the aesthetics and the fluidity of the motion to be superior. That's a huge win for an open source architecture.
But there was one area where it showed a bit of a lag.
Right. Prompt following. The evaluation showed a slight gap there, and the researchers were very clear why. It's a technical constraint with their text encoder.
The part that reads the instructions.
Exactly. It has a limited context length of just 256 tokens. So if your prompt is really long and complex, the model can't quite grasp all the nuances.
So the video engine is stellar, but the instructions sometimes get a little truncated before they even reach it. Closing that gap is clearly a priority.
It is, and it just highlights how interdependent all these systems are.
Okay, so let's zoom out for our final thoughts. The sheer scope of this family is just remarkable. It does text-to-image, image-to-image editing, and these incredible text-to-video generations.
I mean, we've seen examples of animating a popcorn kernel into a fluffy chick or a pumpkin transforming into an elegant carriage.
That technical power is meeting creative possibility at an incredible pace. The engineering depth here, using geometric verification, model souping, AI critics, it's really resetting the standard for open source AI.
It really is.
So what does this all mean for the immediate future?
Well, the current Kandinsky 5.0 is a family of specialists by design. You've got Image Lite, Video Pro, the Flash variants. Each does one job extremely well.
But that's not the end goal.
No. The long-term goal for these researchers, the next frontier, is to consolidate all of these different capabilities into a single, unified, foundational visual model.
What's the true implication of that unification?
Think about it. What happens when one single AI engine can generate a photorealistic image, edit it with your text, and then animate that exact composition into a high-fidelity cinematic clip instantly with perfect coherence?
Without switching between different models or tools.
Exactly. That unified approach completely redefines the entire visual content pipeline. It's moving from a toolbox full of specialists to a single visual genius.
That consolidation of expertise into one brain, that is indeed the next frontier. We hope this deep dive gave you a head start on understanding how this technology is learning the language of cinema.
And what breakthroughs made that possible.
Thanks for joining us.
Our pleasure.